Now we're going to explore complex numbers, but before we dive into those, let's do a quick review of the type of numbers that we typically study. So we spend most of our time dealing with real numbers, but we're going to go even simpler there to the natural numbers. Natural numbers are your counting numbers, 1, 2, 3, 4, etc. Add a 0 to the natural numbers to make it a little bit bigger, and you have the whole numbers. So now we have 0, 1, 2, 3, 4, etc. If we throw in some of the negatives, now we're talking integers. So not only can I go 0, 1, 2, 3, 4, I can go 0, negative 1, negative 2, negative 3, negative 4, etc. And I get this bigger group of numbers known as the integers. We get it a lot bigger when we switch to rational because now we throw in all the fractions, all the things between 0 and 1. A third, a half, a fourth, a tenth. There's a lot of fractions in between each pair of integers, so we have the rationals. And of course, if we have rationals, which include the fractions and the decimals that repeat or end, there's another group that has that has decimals that don't repeat and don't end, known as the irrational. And when you put those irrational numbers and those rational numbers together, we have the real number system. What we're going to add to that today is this group over here known as imaginary numbers. Now there's a smaller subgroup known as pure imaginary, and then the bigger group known as imaginary. But when I take the imaginary numbers and the real numbers and put them together, we get the complex number system. And this is where majority of our mathematics take place, is in this complex number system. Now to talk about these imaginary numbers, we're going to go to something that we've had to deal with along the way, and that's the square root of negative 1. The square root of negative 1 doesn't exist. There isn't a number that I can take times itself and get negative 1, so there's no way to square root this. So what they did is they came up with a name for this, and they gave it a symbol. They called it I. That's an imaginary number. That I is what moves us into this other group of numbers. Now, the interesting thing about I is we can do calculations with it. If I take I times I, then I have this square root that's being squared, and I go from having an imaginary number back to a real number. If I cube it, I actually get a negative I, and if I take it to the fourth power, which would be squared twice, I get back to a positive 1, and again, I'm out of the imaginary number system and back into the real number system. So it's kind of interesting. Now, the other crazy part about these is they cycle. Once I get to 5, it's the same as I to the first. I to the 6th, the same as I squared. I to the 7th, the same as I cubed. I to the 8th, it's the same as I to the 4th. Those answers right there. And it cycles and cycles and it cycles. It's the same as I to the 9th, the same as I to the 5th, is the same as I. So every 4, it just kind of cycles itself. The ones we spend most of our time with are just I and I squared. Okay, so they are going to show up along the way. So I put some examples in here of problems typically we can't do because of the negative, but now I can take care of that negative. And if you want to think of this in two pieces, I could always do the square root of 25. It's a perfect square. This is 5. This thing right here is what's going to make it imaginary. So we just call it 5i. Now, if it's a number I can't do, I'm still going to fix the negative. The 7 I can't do, but the negative I can turn into an I. And if it helps to break them down, break them down. 12 breaks down into a 4, a 3, and a negative 1. Do the parts that you can do. I can do the square root of 4. I now know that the square root of negative 1 is actually I. So I have a 2 and an I. I just have the square root of 3 that I can't do. Now, these are all examples of pure imaginary numbers. There isn't anything being added to it. There isn't anything else there. But when we start adding other things to it, we get into imaginary. And so here's how they talk about them. And I'm going to look at this from two different aspects. A plus bi is a complex number. It has a real part and it has an imaginary part. But when I put them together, we get that complex number. Now the catch is this number here and this number in front of the I are still real numbers. Okay, it's the I that makes this the imaginary part, but those are actually real numbers. So don't get that confused with the real part and the imaginary part. They're still real numbers. They can be any kind of real number, whether it's rational, irrational, natural, whole, integer. It can be anything. So let's do a couple of operations with these complex numbers. They're relatively simple because when we add complex numbers, we're going to go back to when we first learn of combining like terms and take that same approach. These are real numbers. I'm going to put those together. This is the imaginary part, and there's a 1 here. So I'm going to put those together, and I've added 2 complex numbers. Subtracting is the same process. The only trick with subtracting is I have to keep track of my minus sign. If you want to write it without the parentheses, you can. Just remember that the minus sign goes to both parts, so minus and negative actually makes that plus. And we're just combining like terms. 1 and -3, 5i and 2i. I subtracted 2 complex numbers. It's combining like terms. Now let's take a look at multiplying and dividing. So to multiply, we're going to look at a couple different scenarios here. We're going to do one that looks a lot like the distributive property. And it is. We're going to take this 3i and multiply by both parts here. So 3 times -5 is -15, and that I just comes along. When I multiply the other part, 3 times 2 is 6, but I times I is now I squared. So this is why I said we deal a lot with I, square root of -1, and I squared. So now I need to go back in here and realize that I squared is actually a -1. So it makes that 6 -6. And I still have this 15i, and if I write it in that complex form, the real part and then the imaginary part, here is my complex number answer. It gets a little more complicated when there's 2 full complex numbers, but think about when we multiply binomials. Some of us used a box method, some of us used foiling. We're going to take that same approach. We're going to multiply the real parts. We're going to multiply this real part and this imaginary part. We're going to take this imaginary part and this real part. Don't forget the negative. And then I'm going to multiply the 2 imaginary parts, 15i squared, which is a great start. You've got the multiplying done, but we should probably simplify. These 2 things look like terms, so I'm going to put them together. I've got the 8 in front, and then I have this thing. I have to take care of the I squared. I know what I squared is. I squared is -1. So that actually makes this a plus 15. So I have 8 and 15, which are still like terms. And then I have this -2i, and there's my complex answer. Now I'm going to do one more, and I'm going to talk about this in a moment. But I'm going to multiply these 2. So I still have that I squared here, so I'm still going to turn this into a -1, and -1 times -25 makes it a plus 25. That hasn't changed at all. But take a look at my 2 imaginary pieces here. When I go to combine those like terms, one's positive and one's negative. They actually cancel out. So all I have is 16 plus 25. I don't have an imaginary part anymore. I jumped out of the imaginary numbers, the complex numbers, into the real number system. I got 41. So I took 2 complex numbers, multiplied them together, and got a real answer. Okay? The thing that's unique about these two, notice they're the exact same thing except one is a plus and one is a minus. Those are known as complex conjugates. Okay, we've talked about conjugates before, but complex conjugates have this unique characteristic where they jump out of the complex world and get us back into the real. That's going to become important when we talk about dividing. Now, this looks like a fairly easy problem. Nothing wrong with it, it's just a fraction. The problem is we've always gotten square roots off the bottom, and you're probably thinking, but there's no square root in this. There is. Remember, I is just a symbol that represents square root of -1. So there's actually a square root right there. So what we're going to do is we're going to multiply by another I to make this go away. So I'm going to multiply by I on the bottom. Now, I can't just throw an I in there. It's going to change my answer. I have to multiply by something that's not going to change this. That number I pick is actually 1, but I'm going to be very creative with it. I over I is really just a 1, so I'm going to multiply by 1. Now, on the bottom, I get a 6i squared. I'm going to be able to handle that, no problem. On the top, I'm kind of like that first problem. I need to distribute the I. So I get a 4i, and I get a minus 1i squared. I times I gives me I squared. So I have some simplifying to do. I have an I squared here, which is going to be a -1. And -1 times -1 is going to actually make that a +1. And I've got this 4i. I can't do anything with it. On the bottom, I squared, that's a -1. So -1 times 6, that makes that -6. Now I don't have that square root on the bottom. Problem solved. Now, when you look at these, this is fine for my purposes. I don't mind having that fraction, but sometimes you'll see it put it back into that complex form, the form we kind of talked about. I want -1/6 as the real part, and then this would be a -4/6i. They probably reduce that to 2/3. So you may see it written that way, this being the imaginary part. There's nothing wrong with this. There's nothing wrong with it written this way either. They're both perfectly acceptable. Now it gets a little more complicated here, because if all I do is multiply by I like I did up above, that's great, it fixes this one, but then I end up with a 3i over here. I haven't fixed my square root problem. Same thing up here, I'm not worried about the top. So this is where the idea of a complex conjugate becomes important. We noted that when we multiplied two things that were conjugates, all the i's took care of themselves and I got a real number. That's what I want to do here. So again, I'm going to multiply by 1, but I'm going to get really creative with it. As long as the top and the bottom are the same, this is just 1. But notice that my bottoms are conjugates. So when I multiply these out, my i's should take care of themselves. So 3 times 3, that's a 9. Here I get a minus 12i and a plus 12i. And here I get a minus 16i squared. I can handle that. Now let's make sure we did this right. Those two cancel out, good. I squared becomes a -1, so I end up with 9 plus 16. If you need to see that, those cancel. This is a -16 times a -1, that makes that a +16. So 9 plus 16, that gives me a 25. No more square root of -1s on the bottom. That's the problem that I'm trying to fix. Now on top, things aren't going to cancel out, but I still do the same thing. If you are a FOIL person, FOIL. If you like the box method, do the box method. If you want to think of it as distributing twice, whatever works. But I get a 15, I get a minus 20i, I get a minus 6i, and I get a plus. Negative times a negative makes a plus 8i squared. Now I'm going to start with that I squared, because that's a negative 1. So that makes this a negative 8. 15 minus 8 gives me a 7 for the real part. Combine my i's in the middle, I get a 26i for the imaginary part. And this is perfectly fine. You could also write it as a real part and an imaginary part. Both perfectly acceptable. Find one that makes sense for you. Now I slipped a couple of last things in here. We're talking about complex numbers, but I wanted to just tie it into our factoring and solving that we do. Something like this, yes, I can take out a 2, but I was stuck with my factoring. If I change to complex numbers instead of real numbers, now this can be factored. I get an x plus 4 and x minus 4. I just have to put an I in there, and now it factors. That I makes the difference for the sum of squares. Or if I have solving, however you tend to solve things, whether it's by factoring, whether it's by quadratic formula, whether it's by graphing, whatever you tend to do. Now this one is going to work. Let me show you what I mean. If I do the discriminant, b squared minus 4ac, I get 1 minus 24. That's a negative 23. The discriminant is telling me I don't have any real answers. But now that we're talking about complex numbers, now I can do this. X is equal to the opposite of b plus or minus square root. There's the discriminant. B squared minus 4ac all over 2a. I can do this problem now. I know why it didn't have any real answers. It's because of that negative. So if I take that out and put an I in here, I'm going to put it in front so it's easier to see. There's my two answers, my two complex answers, not real answers, but complex.